Welcome to the deep dive. If you have ever wondered why some chemical reactions explode in like an absolute flash, while others just take agonizing days to fizzle out, well, the answer actually lies in a microscopic demolition derby. Today, we are taking our stack of sources, so a specialized guide and its accompanying data charts, to really map out the invisible mechanics of chemical reaction rates.
Yeah, and the fundamental rule driving all of this is what is called collision theory.
Mhm.
I mean, particles can't just touch to react. They have to actually collide with enough energy and in the exact right orientation.
Right, like a chaotic bumper car arena.
Exactly. You don't score any points for just, bumping fenders. A reaction only registers if you have a high-speed head-on collision.
Yeah.
So the core challenge is really engineering the environment to force more of those successful crashes.
Okay, so let's unpack this a bit. If we need high energy impacts, I mean, the most obvious dial to turn is heat, right? Looking at the temperature graph from the data, the effect is pretty undeniable.
Oh, absolutely. Pushing a reaction from 30 to 50 degrees Celsius produces mass exponentially faster.
Because we are essentially giving the particles more kinetic energy, so they move faster and hit much harder.
Right, they overcome that minimum threshold to react. But, if tweaking the temperature isn't an option, we can alter the arena itself.
Like through concentration and pressure.
Yeah, instead of speeding the cars up, we just pack 3 times as many into the exact same rink. This sheer crowding drastically increases the frequency of collisions.
Which makes sense. But the sources actually flag a major misconception here, don't they? People often assume higher concentration makes the particles move faster.
Yes, they do. But it doesn't change the speed at all. It just, well, it makes the traffic worse.
Right. The
Yeah,
individual particle speed stays constant, but because they are so crammed together, they literally cannot help but run into each other.
exactly. But cramming more particles into a space or heating them up, that takes massive amounts of external energy.
So if you are engineering a reaction where you are constrained and you can't really do either of those things, you have to look at the geometry of the reactants themselves.
Yeah, by physically altering materials to expose more targets. The sources illustrate this beautifully with surface area.
I loved that visual. Instead of a solid block, if you fracture that material down, like into a fine powder, the exposed surface area just skyrockets.
Right, the example they use is a 2 centimeter solid cube, which has a surface area of 24 square
Oh,
centimeters.
wow.
But if you break it into 8 smaller 1 centimeter cubes, the exposed surface area suddenly doubles to 48 square centimeters.
Which explains why magnesium powder flashes instantly compared to, like, a slow burning solid magnesium ribbon.
Yeah, the particles are liberated from that rigid outer structure. It is the exact same principle governing why aqueous solutions react so aggressively.
Because when substances are not locked into a solid matrix, they just have infinite angles to approach each other and collide.
Exactly. They can move freely to find each other.
Okay, here's where it gets really interesting to me, though. We have talked about speeding up the cars, crowding the arena, maximizing the exposed targets, but what if we just bypass the arena entirely?
Ah, you mean catalysts.
Yes. Looking at the activation energy chart, does a catalyst act like, I don't know, a microscopic jetpack injecting extra energy into the system?
No, and what is fascinating here is that is a really common mistake. People think catalysts add energy, but they do not.
Wait, really? So what are they actually doing?
Well, instead of forcing the particles to climb over this massive activation energy mountain, a catalyst essentially bores a tunnel straight through it.
Oh, I see. So it provides a completely different alternate pathway that just requires significantly less energy from the start.
Right, it lowers the mountain down to a small hill. And the brilliant part is the catalyst itself is not consumed in the reaction.
It just sits there holding the tunnel open for the reactants to pass through over and over again. That is wild.
It is. So to sum up the mechanics we have pulled from the data today, if you want to dictate the speed of a reaction, you tweak the heat, you crowd the space, you maximize the exposed surface area, or you introduce a catalyst to rewrite the pathway entirely.
Which really
Yeah.
makes you look at your own workflow differently. Since chemical catalysts speed up reactions by boring a tunnel through the obstacle without burning themselves out, I mean, what catalysts could you introduce into your own daily routines? How can you bypass the mountain altogether so your most difficult, high-friction tasks happen in a flash rather than taking hours?